Welcome to the Deep Dive. Today, we're getting into something really fundamental in manufacturing, but maybe a bit overlooked. The deep drawing of stainless steel sheet metal.
Yeah, it does sound super technical, doesn't it? But deep drawing is, well, it's everywhere. It's how we make tons of corrosion-resistant stuff, cheaply and efficiently.
Like, what kind of things are we talking about?
Oh, everything from, sinks in commercial kitchens, surgical instruments, even vital bits for chemical plants, petrochemical stuff, and pretty much anything metal on a boat.
Right. Okay, so it's widespread. And our source today, it's a pretty technical paper looking at how to fix the problems that pop up. Because deep drawing, it sounds straightforward, but it's tricky.
It really is. You're always fighting against defects, wrinkles, nasty scratches, or the big one. The part just breaks during forming.
And that comes down to getting the physics and the material science just right, yeah.
Absolutely. To make it work reliably, you need tight control over things like how hard you clamp the sheet, that's the blank holder force, how fast you deform it, and crucially, the lubrication.
So that's our mission for this deep dive. Understanding how engineers use these advanced simulation tools. FEM, finite element modeling backed up by physical tests, to figure out the best combination of material and lubricant. Those seem to be the key variables.
Exactly. And the goal isn't just tweaking the process. It's about really understanding why things fail. Where does the stress pile up? How does changing the lubricant totally change where it breaks?
That level of detail, you can only really get that with this kind of simulation, right?
Pretty much. That predictive power is what makes this approach so valuable. Okay, let's unpack this.
Right. So let's start with that immediate challenge, lubrication. Why is this so important, and why is it so hard to get right in deep drawing?
Okay, lubrication's got two main jobs. First, stop adhesive wear. That's when tiny bits of the tool and the sheet metal kind of weld together under pressure and then tear off.
Leaving those scratches and grooves you mentioned.
Precisely. Nasty surface finish potentially weakens the part too.
And the second job, you said it was about flow.
Yeah, it's all about letting the metal slide. The lubricant acts like a slippery layer between the sheet and the tools, allowing the metal under the blank holder to flow smoothly into the die cavity.
Which helps spread the deformation out.
Exactly. You get a more even, homogeneous distribution of stress. If friction's too high, the metal just kind of locks in place near the edge.
And all the stretching happens in one small area.
Right. And that leads directly to tearing. But the process itself makes lubrication tough.
How so?
Well, you got these huge shear forces as the metal slides. They literally just push or drag liquid lubricant right out of the contact zone.
So the lubricant film gets thinner and thinner.
Until it breaks down. Then you get metal-on-metal contact, friction skyrockets, and, well, you're heading for failure.
Okay, so to understand failure, we need to grasp how the metal is actually moving and changing shape.
Right.
You mentioned two main ways it deforms.
That's right. Two main modes. First is drawing. Think about pulling something long and thin, like taffy. It gets longer in the direction you pull.
But thinner or narrower side to side?
Exactly. Positive elongation one way, negative contraction the other way. That's typically happening to the metal sliding under the blank holder.
Okay. And the second mode? The more critical one.
That's stretching. This is where you get positive elongation in both directions across the sheet plane at the same time.
Ah, so it's being pulled wider and longer simultaneously.
Right. And because metal volume basically stays constant during plastic deformation, stretching forces a big reduction in thickness.
That sounds like where things are likely to go wrong. Necking and breaking.
That's precisely where it starts. Stretching is much tougher on the material.
And there's a standard test for this, to see how well a material handles that stretching.
Yep, the Erichsen test, or IE for Erichsen index. It's standardized, EN ISO 2482. You basically take a sheet of the metal and push a standard hemispherical punch into it until it cracks.
And the depth it reaches just before cracking is the score.
That's the IE value. Higher IE means better formability, specifically under that kind of biaxial stretching stress.
Yeah.
It's a key benchmark.
Got it. So let's talk materials. This research compared two very common stainless steels, AISI 304 and AISI 430. One's austenitic, one's ferritic. What's the difference in practice?
Well, the tensile test showed some clear differences. Interestingly, the AISI 430, the ferritic one, actually had a higher yield strength.
Higher yield strength, so it takes more force to start permanently deforming it. Around 340 MPa versus 267 for the 304.
Correct. About 340 MPa average for 430 versus 267 for 304.
Okay, wait. My intuition says higher strength is good. Why would that make it potentially worse for deep drawing? Seems counterintuitive.
Yeah, it does seem that way at first. But for deep drawing, just resisting initial yield isn't the whole story. What you really need is good plastic deformability. You want the material to yield, sure, but then you need to stretch and spread that deformation out over a large area without breaking.
And AISI 304 is better at that spreading out part.
Much better. It comes down to the crystal structure. 304 is austenitic, meaning it has a face-centered cubic lattice, or CFC. You can picture the atoms like layers of ball bearings. They can slide past each other relatively easily.
Makes sense. More slippery at the atomic level. And the 430.
That's ferritic, body-centered cubic, or CCC. It's a more rigid structure. Think stacked cubes instead of spheres. It resists initial movement, more hence the higher yield strength, but once it starts deforming, it doesn't spread the load as well. It tends to fail sooner.
And there's a number for that ability to spread the load after yielding.
Yes, the work hardening coefficient, often called N, it measures how much the material strengthens as it deforms plastically. A higher N means as one area starts to thin, it gets stronger, forcing the deformation to move to adjacent, weaker areas.
So it prevents the deformation getting too localized.
Precisely. It distributes the strain. And the study found 304 had a much higher value average, 0.329 compared to just 0.177 for 430.
Wow, that's a huge difference, almost double.
It makes a massive difference in resisting that localized necking that leads to fracture.
Okay, and they used statistics, ANOVA, to confirm these weren't just random variations.
Yep. The analysis of variance showed clearly that both the choice of material and the lubrication used had statistically significant impacts on that Erichsen index, the IE score.
No surprise then that AISI 304 consistently got higher IE scores.
Exactly. Confirmed its better ability to handle the stresses. But the other big finding from the ANOVA was about the lubricant.
What did they find there?
Using a specific type of lubricant, a solid PVC film dramatically boosted the IE score for both types of steel.
So regardless of the steel, this PVC film just made things work much better.
Significantly better. It clearly improved the sliding, allowing more material to flow in from under the blank holder.
That flow seems to be the secret sauce. But here's where the research got really interesting, right? It wasn't just how deep they could draw the cup, but how it failed. The lubrication actually changed the failure mechanism itself?
That's the core finding, really. They mapped the strain patterns across the drawn cups and found two totally different ways failure happens, depending entirely on the friction.
Okay, let's break those down. Scenario 1, no lubricant or poor lubricant, meaning high friction. What does that look like?
When friction is high, the metal flow from under the blank holder is severely restricted. It basically gets pinned down. The strain map shows this distinctive double bell shape.
Double bell.
Meaning you get two zones of high strain concentration, one near where the punch starts bending the metal, and another out near the edge by the die radius. But the peak stress isn't at the very center.
So where does it actually break?
The failure, where the von Mises stresses spiked over 1,000 MPa, happened in the intermediate zone. That's the unsupported area of the cup wall, between the punch head and the die radius.
And the type of deformation causing the failure there?
It was classic drawing. Huge elongation along the cup wall, like 80%, but significant shrinking in the circumferential direction, maybe 10%. The material was being pulled thin in one primary direction until it snapped.
Okay, so high friction leads to drawing failure on the cup wall. Now, scenario 2, low friction, using that effective PVC film, what changes?
Everything changes. With low friction, the material flows easily from the flange into the die. The strain map smooths out completely into a single bell shape.
Meaning the strain just increases smoothly towards the very center.
Exactly. Maximum strain, maximum stress, and the eventual failure point all shift to the apex of the spherical cap, right at the very bottom of the cup where the punch nose is.
Wow, completely different location, and the deformation mode there.
It becomes primarily balanced by axial stretching. The material is being stretched fairly evenly in all directions across the plane at the bottom of the cup.
And you mentioned the stress levels were different too.
Yeah, this was fascinating. In this low-friction stretching failure mode, the von Mises stresses actually reached over 1,200 MPa at the apex before failure occurred.
So higher than the 1,000 MPa peak seen in the drawing failure mode.
Considerably higher, suggesting that with good lubrication, you're actually able to utilize more of the material's inherent strength before it fails.
That ties into the thickness measurements too, right? The FEM simulations showed how the thinning happened over time.
Yes, that gave real insight. Without lubrication, once the initial cup shape forms, the thinning effectively stops under the punch nose. Why? Because no more material can easily flow in to replace what's being stretched.
So the thinning has to concentrate somewhere else.
Right. It rapidly concentrates in that vulnerable sidewall area, the intermediate zone, until it fails. The material under the punch basically gives up early.
But with the PVC film allowing flow,
the thinning continues progressively right under the punch nose at the apex. The entire area deforms together much more uniformly right up until the material reaches its limit and cracks. That's the ideal homogeneous deformation.
Which brings us neatly to the simulation side, the finite element modeling. Why is getting this FEM right so crucial?
Well, the traditional way to analyze this deformation is incredibly laborious. You'd literally screen print a grid of tiny circles onto the sheet metal before forming it.
And then measure how every single circle distorted.
Exactly. It tells you the strain, but it's slow, expensive. You have to do it for every test condition. Just not practical for developing new parts quickly. FEM offers a virtual alternative.
A shortcut, essentially.
A potential shortcut, yeah. But only if the simulation is accurate. And there's a big hurdle here. Standard material models used in FEM often break down once necking starts. They can't accurately predict the final fracture.
Because the simple formulas don't work anymore when the material starts to fail locally.
Right. The actual stress keeps going up even as the neck forms, but the standard engineering stress strain curve calculation fails. So the researchers had to figure out how to model that true stress behavior right up to the breaking point.
How did they crack that?
They used a really clever iterative approach. First, they did physical tensile tests, carefully measuring force and deformation using a camera tracking a grid on the sample, all the way to fracture.
Okay, capturing the real-world failure.
Then they simulated that exact same tensile test in the FEM software. They tweaked the advanced material model parameters within the simulation until the FEM prediction perfectly matched the force, the deformation, and the point of fracture they saw in the real test.
Ah, so they used the physical test data to teach the simulation how the material really behaves at the point of failure.
Exactly. They were essentially reconstructing the missing part of the true stress-strain curve computationally, guided by the physical experiment.
And did it work? Was a final deep drawing simulation accurate?
Incredibly accurate. The validated FEM model predicted the Erichsen index, that key depth measurement, with an average error of less than 3% compared to the actual physical Erichsen tests they ran.
That's remarkable for such a complex process.
It really is.
Yeah.
And crucially, the simulation didn't just get the number right, it also visually replicated the failure modes. It correctly predicted the double bell strain pattern and intermediate failure without lube, and the single bell pattern with apex failure when the PVC lube was simulated.
So the model captured the fundamental physics. That predictive power is huge.
It unlocks insights you just can't easily get for physical tests alone, like seeing exactly how the thickness evolves second by second or mapping the stress distribution. The FEM clearly showed how the 304 steel, with this better work hardening, spread the stress out much more evenly than the 430.
Okay, so let's try and wrap this up. What are the main takeaways from this deep dive?
I think the big story is how interconnected everything is. The material's inherent ability to deform plastically, like 304's advantage, and the friction conditions set by the lubricant. Those two things together fundamentally determine how the part will fail. Will it be a drawing failure or a stretching failure?
And to get a good, efficient process, you need that smooth, homogeneous strain distribution.
Which comes from using a steel that work hardens well, like 304, combined with really effective lubrication, like that PVC film, to maximize material flow.
And the big practical implication.
It's that these sophisticated simulation tools, the FEM, when properly validated like this, are genuinely getting good enough to potentially replace a lot of that slow, expensive, trial and error physical testing during product development.
Makes sense. Faster development, cheaper components, hopefully. So what does this all mean for us looking at these finished stainless steel parts? Here's a final thought. We saw that with the optimized process, the good lube, the stress at failure actually hit 1200 MPa, significantly higher than the 1000 MPa seen in the poorly lubed case. Does optimizing the process so successfully actually push the material much closer to its absolute physical limit? Does it make the process hyper-efficient, but maybe also more sensitive, more on the edge, vulnerable to tiny variations in material batches or temperatures? Something to think about next time you see a complex, deep-drawn stainless steel part.